All right, thank you everybody for coming here. My name is Philip. I'm a PhD student in Amsterdam at QSoft, and today I want to tell you a little bit about some recent work we had titled "Making Existing Quantum Position Verification Protocols Secure Against Arbitrary Transmission Laws." Some pictures of my co-authors, René Allerstover from Amsterdam, who is also here, Andreas Bloem from Grenoble, who is also here at QIP. Then Harry Buurman from Amsterdam, Matthias Christandel from Copenhagen, Jorens Escola-Foras from Amsterdam, and Florian Spilman from Amsterdam. Okay, so to give you a little bit of an outline of my talk, my talk's more related to practical implementation of quantum position verification protocols. So Alex's talk was more about theoretical point of view. So first, I'm going to tell you a little bit about what is quantum position verification and why do we want to use it. Then I want to argue that the task of position verification cannot be done unconditionally secure, which means we are interested, if we want to implement this, in some sort of practical security for quantum position verification, and I'm going to tell you what it means. And then I'm going to introduce a protocol and argue for you that this actually is a very good candidate protocol that has all the properties of security that we will be practically interested in. Okay, so what is the task of position verification? Often it's depicted in a single line. So suppose you have two verifiers, V0 and V1, that want to verify the position of an honest prover called P. And let's say they're on a line, and the prover P is right in the middle of two verifiers, V0 and V1. That's depicted here. This is the position. Now what can they do? They can send him, they can ping him. They can send a message from both sides with the speed of light. They ask the prover to do some operation on this message, and then he has to send something back. And then they can check whether the answers was according to what they wanted. And they can check if the answers were actually received in time. And this is a way to verify somebody's position. This can be used to build further cryptographic schemes upon. Like you can use this to authenticate a public channel, for example, is an idea often. So to give you an example of quite a simple, maybe a protocol that would come up immediately is, suppose one verifier sends a BB84 state. So here, sorry, the squiggly line is actually a message being sent. The squiggly line indicates that it's a quantum message. A straight line here is a classical message. And they have sort of a 45-degree angle as a light cone, so it means that these are sent with the speed of light. Suppose verifier V0 sends a BB84 state, so in either computational basis or Hadamard basis, and from the other side, the prover gets the information in which basis the qubit is encoded. Then the task for the honest prover here is to measure in the correct basis and communicate the answer out to the verifiers. And then you want to argue that this is a task that can only be done at that point in space-time, right? Because you need both the qubit and the classical bit to do that. And then another point of view is, what is an attack on position verification schemes? Well, an attack is actually when a coalition of attackers, here they're called Alice and Bob, convince the verifiers that there was somebody at a claimed location, even though there was nobody there. So if you consider the previous picture, suppose they send in this BB84 state and the base from the other side, but there's no prover P at all. So now the coalition of attackers wants to convince the verifiers that there was actually P. So what they do is they can do some operation. They can split their quantum information and keep something for themselves in time, send something over to the other attacker, and the other one can do it as well. These messages can be quantum. And then the attackers will send out the answer just in time to fool the verifiers. Right, so this is sort of the general form of it that an attack would have. And it turns out that if the attackers pre-share enough entanglement, that they can actually implement any position verification protocol. This is a result. And with enough here, I mean, you can do it always if you share an exponential amount of entanglement where it grows exponentially with the input size. So, for example, in the case that I described earlier, this BB84 protocol, you can just do this for yourself if you want to try it out. You can see what happens if the attacker A immediately teleports the qubit over to attacker B. Of course, attacker B will then have a qubit with some corrections on it, but he can you can actually argue that he can immediately measure in the correct basis, and even though his answer is not then going to be wrong, when he later learns the teleportation correction, he can actually modify his answer, and then both parties can answer just in time the correct answer. So since we can attack any QPV protocol given enough entanglement, we're sort of interested in proving more of a practical security, right? Because having an exponential amount of entanglement is still a difficult task. So what can we do with that? So to formulate something that we want for practical position verification, you can think of the following. So what properties should such a protocol have? Well, one of them, a protocol should have the following properties. One of them, it should be as simple as possible for the honest prover. You don't want the honest prover to do a very difficult computation, because the longer it will take him, it doesn't really work anymore. Then the uncertainty about where his location will actually be will keep on growing. You want this operation to be almost instantaneous, to be really certain of his location. Furthermore, you want the protocol to be as secure as possible against entangled attackers. And now some more practical things come to mind. You also want the protocol to be secure against some form of slow quantum communication. Actually, you would like to send your quantum information with the speed of light. So what would that mean? That would mean that you send your quantum information through free space. That's basically impossible if you want to do it over longer distances. Then none of your photons are going to arrive, or none of your signals. So you maybe want to do this through fiber or through some network. However, in glass fiber, the speed of light is roughly 2/3 the speed of light in free space. So if you consider yourself to be sending messages through a fiber, how can you prove security against attackers who maybe have access to some exponential, or to some channel that has the speed of light, right? So you want protocols that are secure against any speed of quantum information. And then lastly, a protocol should be tolerant against photon loss. And this is an important aspect, is that most photons that will be sent will actually never arrive. You might be talking about loss rates of like 1 in every million photons, or even less will arrive. So as I was describing the protocol, I was saying there's two answers. You know, they're going to give this BB84, they're going to measure, and then they're going to get a 0 measurement outcome or a 1 measurement outcome. But most of the time, he's actually sort of going to say, I didn't receive anything. And you should always assume, of course, that an attacker has better resources than you. So an attacker can use this to his advantage. An attacker can, for example, guess a basis, and when he guessed wrong, he says, oh, the photon didn't arrive. So if you want to have protocols that are secure in a practical setting, you need to also be secure against this photon loss thing. And this is of importance in this talk. So we focused on, because there are protocols known that are very simple. They're relatively secure against entangled attackers, and they were secure against low quantum information, but they were not secure at all against photon loss. There were also protocols known that were quite secure against entangled attackers, secure against low quantum information, and secure against photon loss, but the operation the honest prover had to do was not simple at all. It's a very difficult operation. So to highlight the first protocol that had these first three properties that I said, it was not secure against photon loss. This is a BB84 protocol type still. But now the basis in which the honest prover has to measure will be determined by two classical strings, x and y, and some Boolean function, f of x, y. So you have to compute some Boolean function on your inputs x and y, then you get some outcome 0 or 1, and that determines in what basis you need to measure the quantum input that you will receive. Some nice properties of this protocol: it's actually secure against slow quantum information. So here I described the quantum information as not going with a 45-degree angle, and it basically means the qubit can come with any speed. But the point is that before you learn this x and y, this qubit is sort of useless to attackers. They cannot do anything to it yet, because it's a maximally mixed state. And so the moment it receives this x and y, something interesting can happen. And x and y are just classical messages that we can send with the speed of light, with radio waves or whatever. That's something that we can do for a long time. Furthermore, what's nice about this protocol is that for a function f, actually here f is then a random function, there are some nice lower bounds known in the classical input size n, so that you can show that you need at least a linear amount of entanglement to attack this protocol successfully, linear in the length of x and y. And of course, from a practical point of view, sending longer classical strings will probably be much easier than attackers pre-sharing more entanglement. So this is sort of a nice property already. But yeah, this protocol is highly insecure against guessing attacks, because what could attackers do? Attackers can simply guess the basis. And then if they guessed wrong, they say, oh, we didn't receive a photon. So if your photon rate is actually lower than a half of the photons arriving, there's a sort of a trivial attack on this. And now in our work, we present a new idea that circumvents the main problems here around photon loss. Namely, we introduce a commitment round in which the prover commits to playing when he receives the quantum information, and slightly afterwards he will receive the basis information, the classical information that denotes the basis information in which he has to measure. Basically, from an attacker's point of view, what this does is it forces the attackers to commit to playing around before knowing all of the classical information. So this sort of eliminates the idea of using a guessing attack. Of course, this is sort of a different setting, right? So we have to see what this sort of would mean for security proofs. So let me draw you first a space-time diagram of what I just described. So again, there's going to be quantum information that comes in, can come in at any speed. Then an honest prover will now do some sort of photon presence detection measurement, and then declare, oh, I received my photon, and then he's going to store it for a little while, a little time delta, and then after this time delta, he's going to receive some classical input, x and y, and then he's going to measure this photon in that basis. And so, from an attacker's point of view, the idea is now that this does not allow them to say loss anymore. So if an attacker has to commit as well, then he has to then afterwards, after committing, output an answer to the verifiers. Right. Okay, so how does this picture look from the point of view of an attacker? Well, now an attacker has to do two things. He has to also give a commit bit. So this is sort of the framework that in which attackers now can operate. So the quantum information can be spread out as they like because it's slow quantum information. And then one attacker, your attacker A, receives classical information X, and the other attacker B will receive classical information Y. And locally, they both have to decide on committing based on only that information. So CA here, you can see, it can only depend on X, because X is in its previous light cone and Y is actually not there at all. So Y, the information of Y can never reach CA, so CA is independent of Y. From the other point of view, CB is actually independent of X, because the information from the other side never reached CB. But what do we know about these commit bits? They have to be equal, right? An honest prover, if he will commit, he will not send different commit bits to both verifiers. So we know CA and CB have to be equal to each other, while CA can depend on X and CB can depend on Y. And it's precisely this structure that we used in our proof to argue that actually this does not give the attackers much more power. And we show that attacking such a protocol is no easier for attackers than attacking the underlying protocol. And this is formalized in our following main result, which has the following. It says also something about the convergence. That's why I would like to edit here that the convergence isn't even that bad. It says, suppose we play this commit version of BB84 until we have 320k cubed rounds in which both parties commit to playing. So you sort of throw away all the rounds in which they didn't commit to playing. You're not interested in the answer anyway. Then either one of two things is going to happen. Either the attackers are going to be detected with probability bigger than some 1 minus 10 to the minus 9 by means of different commits. So by super high probability, you're going to see different commits. And if you see different commits, you can immediately abort because you know you're being attacked. Or we're going to have a bound on attacking the commit BB84 protocol in a single round in terms of the original probability of attacking the BB84 protocol in a single round. So we say that the probability to attack the committed version of QPV BB84 converges to attacking the original underlying protocol inversely in K. Right, so we actually inherit the security of the original underlying protocol. Now, what is nice about this is that you sort of circumvent the issues of loss, but of course I introduced something new, right? I said the prover now needs to do a photon presence measurement, photon presence detection scheme. Actually, this is sort of highly unlikely that on a large scale, very quickly in succession, you actually can do such measurements, because doing a photon presence detection measurement is very difficult. There's state-of-the-art setups that can achieve something like that, but we would like something a little bit more practical, because that's how our ideas were envisioned here. And in that sense, we realized that we don't even need to always detect a photon. We're perfectly happy if you only detect a photon with some rate, but if you detect it, you need to be sure that the photon was actually there. And we propose an experimental setup that we call a poor person's lossy photon presence detection setup, where the idea is the following. The prover continuously makes EPR pairs, and he does a Bell state measurement on any incoming signal. So he's sort of continuously doing Bell state measurements, and sometimes when the photon arrives, he will have a Bell state measurement that succeeds, and then he knows that that the incoming photon actually teleported to the other half of the Bell state that he kept somewhere else. So he sends half of the Bell state into some sort of memory, and the other half he sends over, and then he does a Bell state measurement there. And when his Bell state measurement succeeds, he commits to actually playing, and then he will receive a little bit later the classical information XY, and he will do the correct measurement on the other half of the original EPR pair. Of course, he has to do the teleportation corrections on it first. And you can implement this in a linear optics fashion with beam splitters and all that stuff. So then you can actually do a partial Bell state measurement with very high rates and almost perfectly half the time, for example. That's not a difficult setup. And this half the time doesn't interest us, because the half the time that you Bell state measurement doesn't succeed, you actually are not committing anyway, so it doesn't introduce any error. So what are the experimental requirements for this? You need to be able to make EPR pairs on demand, you need to do a par state Bell measurement, and you need some sort of quantum memory in which you're going to store the other half of the Bell state. Now, quantum memory is actually a more difficult thing, but we argue you don't really need a quantum memory. You more need something like a quantum delay. You need to store it a little bit until the classical information comes in. So what you can do, you can also shoot it into a fiber, and you just let it go in a loop through a fiber a little bit, and then it comes out after some fixed time. And this is actually much more easier to do in an experimental setup than a full quantum memory. And then afterwards, when it comes out of this fiber, you need to do some sort of fast switching, depending on the classical outcome of the function f of xy. So you need to then decide, I'm going to do computational basis or Hadamard basis measurement. But the nice thing about all of this is now I'm putting requirements on what the prover has and the setup of an honest prover. So we're mitigating something that is not in control of the prover, namely the channel that you're using and the loss that will happen on this channel, to the prover side, where he can, we argue it's even not that hard for him to do, but where he can set up his setup exactly as he likes and with the right parameters, and he can check whether all the parameters are correct. Okay, so in summary, what have we done? We've presented the committed version of a QPV BB84 protocol, and we show that it inherits all the security properties from the original BB84 protocol. And it is, on top of that, secure against photon loss. Thus, it has all these 4 properties that I described in the beginning. We do this by introducing a commitment round in the QPV protocol, which forces attackers to commit to playing before they can use a guessing attack. As our main result, we show that when played over a large number of rounds, the probability of attacking a single round of this committing BB84 protocol converges to attacking the original BB84 protocol in a single round. So the security is inherited. In fact, our method doesn't really need to use anything of the QPV BB84 protocol in particular, but it only needs to use the fact that it was already secure against slow quantum communication. So in fact, we've shown that any protocol that is secure against slow quantum communication can be sort of augmented to be also secure against transmission loss if you allow for this commitment round to be played. If you slightly alter it to add a commitment round. What else would we like on top of this if we're really going to implement all these things in practice? Well, I said we have this linear lower bound on entanglement, but this is only for random functions. But it's also only linear. Can you get this linear lower bound up? We suspect you can do actually a little bit better than these linear lower bounds, or maybe you can actually show that you need an exponential lower bound to do these functions, which is sort of related to the previous talk. Furthermore, of course, computing a classical random function is going to take a lot of time. So we would like to have lower bounds on concrete functions. So for example, inner product function, the best lower bound is log n entanglement that you need at least to attack it. And we suspect you can actually do better than this, but it will be a nice way to prove. And if you prove it, you immediately can use the rest of the tools we have shown here. And it would be nice if you can bring our result into a parallel repetition world where you can say, okay, I'm going to play a lot of rounds at the same time, and I'm just going to see on which rounds an honest prover is going to commit. And if you then can show that the probability to do this successfully scales exponentially with the number of rounds in which he commits, that will be a super nice result, because then from a practical point of view, all these things will combine really nicely. And with that, I'd like to thank you for your attention.
Thanks, Philip, for the nice talk. Okay, if you have questions, please come to the mic. So, do you want to tell us about the connections with black holes?
Yeah, yeah. I don't think there's any connection with black holes. It was purely of a practical cryptographic interest to us, and to still show security beyond QKD in some interesting cases.
Any other questions? Yeah, there's one question coming up.
I have a probably somewhat straightforward question. So the first adaptation was though that you can have these slow quantum signals, but as far as I understand, you still need to go the classical messages need to go almost at the speed of light.
Yeah, that's correct. Yeah.
From a somewhat devil's advocate perspective, if you can send these like. The problem was that, okay, yeah, maybe we have these slow quantum signals, but then why aren't the classical messages also too slow?
Because it's very easy to send fast classical messages. We do it all the time. The radio waves, for example, go with the speed of light. So yeah, sending somebody a classical message with the speed of light wouldn't be that hard.
So in the diagram you had the output was always classical. Is the issue that it's impossible to have a position verification scheme that's slow against that's secure against slow quantum output?
Yeah, that's a good point. Yeah, you kind of want your output to not be quantum, right? That the prover has to send back to the verifiers if you don't have access to quantum channels that have a speed of light. So yeah, if you would do F routing, for example, then a prover has to route the qubit to the left or to the right. Then he would need to send it with the speed of light, otherwise the timings wouldn't add up, and you wouldn't be sure. So yeah, the BB84 protocol, the output is classical, so the prover can send these outputs with the speed of light. Yeah.
I see, and we know for sure that if the output is quantum, then it can't be secure against slow quantum communication.
It will be interesting to think about. But yeah, here we go from the starting point that your channels don't have speed of light for quantum information. So yeah, you would need to circumvent that somehow. And this is a very easy way to do that. Yeah.
Okay, thank you.
So maybe you said this and I just didn't really get it up properly, but just kind of the security proofs you have also for the original protocol, are they against like individual kind of IID attacks or also against like some kind of collective attack if you do them kind of a multi-round version?
I think for the original protocol, they're for single rounds. Yeah, I don't think they hold yet for parallel repetition.
And that's also what you translate then for this protocol. That's the only thing you show.
Yeah, so I haven't said anything about security. I've just said if the underlying protocol is secure, then this protocol is going to be secure as well.
Yeah, thank you very much.
Any other questions? If not, let's thank the speaker.